and we are into the concept of differentiation of an integral. Whenever we start to speak about the concept of differential of an integral, we always end or lead to speak about the fundamental theorem of calculus. And we have two questions to answer now. For the very first, we have, when does integral of f dash of x over ab to be same as f of b minus f of a? And for the next, as a differentiation of an integral, we have, when does the differentiation of the integral f of t dt to be same as f of x over ax? So the answer for these two questions is, generally this is not true for all functions except the class of functions called absolutely continuous functions. So the answer to these both questions is, this is not true for all f in general, and except the class of functions called absolutely continuous functions. And we will head into the concept of absolutely continuous functions at the end of this chapter. And next, getting into the next concept, we have, if I have f to be integrable function, say on an interval ab, I have f to be an integrable function on the interval ab, and I will define a function, say f, to be integral of f of x, say f of t over ax, then I will show that f dash of x will be equal to f of x almost everywhere. In order to show that f dash of x equal to f of x almost everywhere, I need the help of three lemmas, and we will start to establish those three lemmas now. So we are into the lemma 1 now. It states as follows: if f is integrable on ab, then the function f defined by f of x to be the integral of f over ax is a continuous function and is of bounded variation over the given interval. So if f is defined as follows, where f is integrable, then we need to prove that f is continuous and f is of bounded variation. So heading into the proof, if you remember, in the unit 2 we had a theorem which states as follows: if f is integrable over a set E, so we have f to be integrable over a set E, then given epsilon positive, there exists a delta positive such that for every subset A of E with measure of A to be less than delta, we have integral of f over A to be less than epsilon. We have proved this in the previous unit, if you remember. So it states that if f is integrable over a set E, then given epsilon positive, there exists a delta positive such that for every subset A of E with the measure of A to be less than delta, we have integral of f over A to be less than epsilon. So we need to prove two things here. One is f to be continuous and f to be of bounded variation. So by this theorem, directly it proves that f is a continuous function. So f is a continuous function and it follows by this theorem. Now we are left to prove with f to be of bounded variation. To prove f to be of bounded variation, I will consider a partition, say x1, x1, x0, x1 and so on up to xn of AB. So having a partition of AB, now I will consider the summation of mod of f of xi minus f of xi minus 1, I running from 1 to n. And if you observe, this is nothing but this is same as summation I from 1 to n mod of integral of f of x, where x is running from xi minus 1 to xi, or this can be f of t dt. So this is same as integral of xi minus 1 to xi, where t is defined over xi minus 1 to xi, and this is clearly less than or equal to integral of mod of f of t dt, where again integral is from xi minus 1 to xi. Now having this to be less than or equal to this, if you observe the xi minus 1 to xi, the summation is running over 1 to n, and this is nothing but this is same as integral over the complete interval a to b. So as here we have xi minus 1 to xi, the integral, and summation is running from 1 to n, we have this to be the whole of the interval. So now integral is over the whole of the interval ab. So we have this to be equal to integral of ab of mod of f of t dt. And clearly this is finite. So we have a total variation of f over ab to be less than or equal to this, which is finite. So total variation is finite. So that implies f to be of bounded variation over ab. So this completes lemma 1. Next we have lemma 2. If f is integrable on ab and integral of f of t over ax is 0 for every x in the interval, then we have f of t to be 0 almost everywhere on the interval. Come again, if f is integrable on the interval and integral of f of t over ax is 0 for every x in the interval, then we have the function to be 0 almost everywhere on the given interval. So let me come into the proof. And in order to prove that f of t equal to 0 almost everywhere on the interval, I will consider a set of the type, say set of all x in the interval ab, where f of t is greater than 0. So I need to prove f of t equal to 0 almost everywhere on the interval ab. So I am considering a set, say E, which is set of all x in the interval, such that f of t is greater than 0. Now I will prove that the measure of this set, which is E, measure of E to be 0. Similarly, in the next, I will consider a set x, E, to be the set of all x in AB, such that f of t is less than 0. So considering the set of all x in the interval such that f of t is less than 0, again I will prove that the measure of this set to be 0, that is measure of E is 0. So if I prove measure of E to be 0 in both these cases where f of t is greater than 0 and f of t is less than 0, it implies that f of t should be 0 almost everywhere. So the proof is by this method, showing a measure of E when in two cases. So if I prove measure of E to be 0 when f of t is greater than 0 and f of t is less than 0, then that implies f of t must be 0 almost everywhere. So for the first case, I will prove in the case that f of t is greater than 0. So now I need to prove that measure of E to be 0. And the proof is by the method of contradiction. So we will assume that suppose measure of E is greater than 0, and I will arrive at some contradiction and we will see what would be. So I need to prove measure of E to be 0, and I am assuming measure of E is, suppose measure of E to be greater than 0. Then if measure of E is greater than 0, then there exists a closed set, say F, which is a subset of E with measure of F to be positive. So if I assume measure of E to be greater than 0, there exists a closed set, say F, which is a subset of E with measure of F to be positive. In particular, if I consider a positive epsilon, there exists a closed set f of E with measure of f positive, so that f is a subset of E with measure of set to be positive, where measure of E minus f will be less than epsilon. So if in particular, if I consider an epsilon to be positive, there exists a set f subset of E with measure of f to be positive, such that measure of E minus f will be less than epsilon. Having measure of E minus f to be less than epsilon, I have measure of E to be less than measure of f plus epsilon. So now I have measure of E to be less than measure of f plus epsilon. Now I will set O to be open interval AB minus the closed interval which I have obtained now minus f. So I am setting set O to be equal to open AB minus f. And since f is a closed set what we have got, and this is an open set, O must be an open set. So now we have O to be open set. Now clearly having O to be AB minus f, now I can have AB to be nothing but O union f. So setting O to be AB minus f, now I have the open interval AB to be O union f, and also we have O intersection f to be empty. So now I have this to be disjoint union. So now if I consider integral of the function f over the interval AB, since this is a disjoint union, the integral of f over AB is same as integral of f over O plus integral of f over f. So now I have integral of f over AB to be integral of f over O plus integral of f over the closed set f. But this is given as 0. Integral of f is given to be 0 in the theorem. So this is 0. Since this is 0, we have now integral of O over f to be equal to minus of integral of f over f. So we have this to be equal to this, as this is disjoint union, but we have integral of f to be 0 as given in the statement of the theorem. So we have now integral of f over O to be minus of integral of f over f. But the strange thing you have to observe here now again, this is not 0. So this integral is not 0 because integral of f over f, where measure of f is positive. So we have measure of f to be positive, so this integral cannot be 0. So now I have integral of f over O to be not equal to 0. But given O to be an open set, O is the countable collection of O is the disjoint union of countable collection of O is the disjoint union of countable collection of open intervals. Say I will consider an, bn. So I have O to be the disjoint union of countable collection of open intervals. Having this, now I can have integral of f over O to be integral of f over O to be same as summation of integral of f over those intervals, say an, bn, where n is running from 1 to infinity, and this is not equal to 0 as integral of f over O is non-zero. So since this is non-zero, this implies integral of f over an bn is not 0 for some n. So we have this to be not 0 for some n. Again, this to be not 0 for some n, we have integral of f to be not equal to 0 for a n bn implies integral of a n f is not 0, or integral of a bn, integral of f over a bn is not 0 for some a between the intervals a n bn. So if I have this to be non-zero, so that implies for a and bn, for some a in that interval, f to be non-zero for a an or a to be non-zero for a bn. But this itself is a contradiction to the fact that integral of f is 0. Given that integral of f is 0 for every x in ab, we are arriving at the case that integral of f over an is 0 or integral of f over a bn is 0, which is a contradiction. So our assumption at the start that measure of e is greater than 0 is false, so that measure of e must be equal to 0. Clearly, again, in the same way, if I assume measure f of t less than 0, I will arrive at the same contradiction, and on the same lines we have measure of e to be 0 also if f of t is less than 0. So if measure of e is 0 implies that f of t should be equal to 0 almost everywhere on the interval ab. Finally, we have lemma 3, which states that if f is bounded and measurable on the interval and f is defined as integral of f of t over ax plus f of a, then f dash of x is equal to f of x almost everywhere in the interval. So f is bounded and measurable on the interval, and if f is defined as follows, then we have f dash of x to be equal to f of x almost everywhere in the interval. So coming to the proof, if f is defined as follows, clearly by lemma 1 we have f to be of bounded variation. So if f is defined as this, by lemma 1 we have f is of bounded variation over the given interval. And since we know that a function of bounded variation is differentiable almost everywhere, we have f to be differentiable for almost all x in AB. So we have f to be bounded variation, and that implies f to be differentiable for almost all x in the interval. And given that f to be bounded, I take let f to be bounded by k. So I assume that I take f to be bounded by k. Then I define fn of x to be f of x plus h minus f of x by h, where h is 1 by n. After having f to be bounded by k, I define fn of x by f of x plus h minus f of x by h, where h is 1 by n. So again, I clearly have fn of x to be same as integral of f of t dt, where integral is over x plus h. So this is same as this. So fn of x is I have the integral of f of t over x plus h. Since f is bounded by k and fn of x is equal to this, also we have fn of x to be bounded by k. So f is bounded by k, and also since therefore we have fn of x also to be bounded by k. And since fn of x converges to f dash of x almost everywhere, since fn of x converges to f dash of x almost everywhere, I can take the help of bounded convergence theorem now. So fn of x converging to f dash of x almost everywhere implies by bounded convergence theorem that we have integral of f dash of x over AC, say C to be a point in interval AB, to be equal to limit of integral of fn of x over AC as n tends to infinity. And this is same as limit of integral of, and since fn of x to be defined as this, f of x plus h minus f of x by h over AC as h tends to 0. So since I have fn of x converging to f dash of x almost everywhere by boundary convergence theorem, I have integral of f dash of x to be limit of fn of x, and which is same as limit of fn of x to be defined as such as h tends to 0. And this is same as now limit of h tends to 0, f of x plus h minus f of x by h is same as limit of h tends to 0, 1 by h integral of f of x plus h over AC minus integral of f of x over AC. And now again this is same as limit of f of x over a plus h and c plus h minus integral of f of x over AC. Now I will split these two integrals by the way that this is integral of f of x from a plus h to say c, and then this will be integral of f of x from c to c plus h, so that again I will split this integral to a plus h, so that this will be f of x, and plus into minus, this will be integral of f of x from a plus h to c. So having get splitted the integral like this, these things gets cancelled. So I am remaining with limit h tends to 0 of 1 by h as integral of f of x over c to c plus h minus integral of f of x over a to a plus h. And observe that since f is continuous, I have this to be equal to f of c minus f of a. That's a limit of h tends to 0. I have this f of c minus f of a, and again this I have to be equal to integral of f of t over a c f of t dt. So I have from f to be continuous, I have this to be equal to f of c minus f of a, and again that implies that to be equal to integral of f of t dt over ac. So now this will suggest us that what f dash of x to be equal to f dash of x, which is same as integral of AC over f dash of x minus f of x dx to be equal to 0. Since integral of at dt over AC is f dash of x minus f of x dx, that to be equal to 0. So by lemma 2, we directly have f dash of x equal to f of x almost everywhere. Now with the knowledge of those three lemmas, we are capable to prove this theorem, and the theorem states as follows. Let f be an integrable function on the interval, and suppose f of x is defined as this, then f dash of x equal to f of x almost everywhere on AB. So we have f to be integrable over an interval, and suppose f of x is defined as integral of f of t over ax plus f of a, then f dash of x equal to f of x almost everywhere on AB. So having the knowledge of those three theorems, the proof it follows. And without loss of generality, we can assume that f to be a non-negative functions. So without loss of generality, I have f to be a non-negative function, and I will define fn of x as follows. So fn of x will be equal to f of x if f of x is less than or equal to n, and it will be equal to n if f of x is greater than n. So having defined fn of x to be f of x, if f of x less than or equal to n, and n if f of x greater than n, clearly we have f minus fn to be also non-negative. F minus fn is non-negative, and fn's are bounded measurable. Fn's are bounded and measurable functions. So clearly I have defined fn, and f minus fn is greater than or equal to 0, and fn's are bounded and measurable. Now by lemma 3 I have the previous lemma what we have proved, the differentiation of the integral of fn of t dt over the interval ax to be same as the differentiation of integral of fn of t over ax to be same as fn of x almost everywhere. So this is what we have learned in lemma 3. So the differentiation of fn over ax is equal to fn of x almost everywhere. But this is same as f dash of x to be equal to the differentiation of the integral of f of t over ax. So this is same as f dash of x to be equal to the differentiation of the integral of f of t. Again, this is same as, I will split the integral as f minus fn over ax dt plus d by dx of integral of fn over ax. So I am just adding and subtracting fn, and clearly this is greater than or equal to the differentiation of a to x fn. So since I have splitted this, and this will always be less than or equal to the differentiation of integral of fn, and this is equal to fn of x almost everywhere. So this is nothing but this is equal to fn of x almost everywhere. So I have in my hand now f dash of x to be greater than or equal to f of x almost everywhere. So I have f dash of x to be greater than f of x. Consequently, integral of f dash of x will be greater than or equal to integral of f of x over ab. As I have this, I also have f dash of x to be greater than or equal to f of x, integral of f of x. So this is nothing but integral of f of x greater than or equal to, this is equal to f of b minus f of a. But I always have integral of f of b f dash of x to be less than or equal to f of b minus f of a. So these two inequalities imply integral of a to b f dash of x dx to be same as f of b minus f of a. So having the integral of f dash of x to be equal to f of b minus f of a, now I can write this as integral of f dash of x to be same as integral of f of t over ab. So if I write this, now I can again write this as integral of ab f dash of x minus f of x dx equal to 0. And since this is greater than or equal to 0 almost everywhere, f dash of x minus f of x is greater than or equal to 0 almost everywhere, I do have f dash of x minus f of x equal to 0 almost everywhere. And since f dash of x equal to f of x is equal to 0 almost everywhere, I have f dash of x equal to f of x almost everywhere, which completes the proof of the theorem.